Hey guys, we're going to be talking about electric fields and electric forces. It's kind of a bummer we're not in class because I got a lot of cool demos for this. And, maybe if we go back in May, I'll still do some of the demos. That would be cool. Anyway, this is how this works. So electric fields, electric forces are a thing. You've probably experienced electric fields. If you've ever been shocked by something, you can feel the hairs on your arms stand up, or if you have a bad hair day. I'm having a bad hair day right now. Anyway, electric fields are a thing. This is where the whole idea behind static electricity comes from. Lightning is just a very large example of static electricity. Things can be charged. So things can be positive or negative. Why are things charged? I don't know. It's one of those mysteries of nature. Things can be charged. All kinds of things can be charged. You have charges. What are charges? They can be little specks of dust. You and me can be charged. Usually things that are negative charges could be like, electrons, and positive charges could be protons. So this is a thing. This is what we think electric fields look like. We're really not sure, but we draw them like this. These are vectors that you see on the screen here. When the field lines are closer together, you have a strong field, and when they're further apart, you have a weak field. Notice that field lines come out, or they originate from positive charges, and they terminate on negative charges. And so magnetic fields look very similar. In fact, they're really kind of the same thing. So anyway, I put a positive and a negative charge here, and you can see our field. Notice that the field can move, which is really cool. But negative charges always have the field lines coming into them, right? Positive charges always have field lines going out. And so here you go. Now, this is a thing, and I want to do something here. So let me get this to work. So gravity fields, we live our life in a field. We talked about this in class. Gravity fields, we have this field we live our lives in. It's called our gravity field, right? And we talked about how do we know which way the field goes. You can take something that you don't care that it breaks, like a marker, and you can just put it out in space and just let it go, right? And it will fall, or I don't like that word, it will accelerate down towards the center of the Earth. And so we can draw a vector representing this. Of course, I have you guys trained. That's the gravitational force due to Earth, yes, on that particular thing. So, this is a thing. Now, what G is, it's actually called our gravity field strength. If I divide both sides by m, then I get this equation G equals Fg over m. This is our gravitational field strength equation right here. You take the force of gravity between two things and divide by the mass of that thing, and you get what G is. Now we know what G is here on Earth. 9.8 meters per second. It's an acceleration. So we know this. Electric fields act the same way. If you have an electric field, it could have a strength. But instead of Fg, it's called Fe for F electric. Instead of a mass, you have something called a charge. And we call that Q. So our little charge called Q, and instead of G, it's called E. So G is our gravitational field strength. E is our electric field strength. And both could be represented as vectors. In fact, I was just showing you that all those little arrows are just vectors, same deal. If I divide both sides by Q, Q is our charge. And we get a very similar equation to this, but instead of G, it's E. Instead of Fg, it's Fe. And instead of M, it's Q. and that is our electric field strength. And that's a thing. So that's how you find electric field strength. There you go. So, just like gravity fields, in order to know what's going on with our gravity field, like I was saying, you take your test mass and you put it out there and you just let it go, right? On an electric field, you can do the same thing. You can take a little, what's called a test charge, and you stick the test charge out there. So we can take a test charge and put it somewhere, and that test charge will show us what's going on. Test charges are always positive. Notice this would make sense. Here, our test charge, this vector represents which way that test charge is going to go. Well, it's going to be repelled from the positive charge because it itself is positive. Like charges repel, opposite charges attract, so it will be attracted to the negative charge. So that is our test charge. So just like putting a mass out there and seeing what it's going to do, kind of the same deal. I want to show you all this. This is a thing. We can separate charge, and this is really where static comes from. And I would have done this in class if we were in class. Take a balloon, which typically can really attract charge, and you rub it against clothing. And what happens is you can actually transfer all the negative charges from the sweater to the balloon. Pretty cool. And now you've separated charge, and this is the essence of static. This is the essence of how lightning works, right? If I let this thing go, boom, it's attracted. All the negative charges are attracted to the positive charges. You can also get it to stick to things like the wall, because it's all of these little negative charges will be attracted to the positives in the wall. So that's a thing. Pretty cute. All right, now, because we have things that are actually going to move, see how this balloon actually accelerates towards stuff, then we must have a force. So I want to talk about this. Just like there's gravitational force and there's gravitational fields, there's electric fields and there are electric forces. So when you're talking about the nature of electric forces, electric forces are like Coulomb's law. Coulomb's law is named after someone. He's dead. Coulomb's law is essentially how you calculate electric forces between things. So we have these two charges. This is usually how I draw charges, and they can be positive or they can be negative, right? And I just draw them like little circles. So Q1, I made a positive charge. Q2, I made a negative charge, right? And this is how you calculate the electric field, the electric force between these things. Now, what's going to happen when you let them go? Well, they're going to go whoop, right? In other words, there would be a vector going this way, and a vector going that way. So they would be attracted. So those are your two Q's. Now, the unit of electric charge is called the Coulomb. We don't normally use coulombs, we use micro or we use nano. We usually use something small, but that's the unit for electric charge. So something can have a lot of charge or can have a little bit of charge, and it's a lot like moles. It's a very ambiguous type of thing. Just know that some things can be charged, everything, and they'll have a lot of charge, they'll have a lot of coulombs, or they'll be not much charge, and just a little bit. So Q are your two charges, and that's measured in usually coulombs. K is called the Coulomb's constant, and it's a very large number, 8.99 e to the 9th. It's a constant. R is the distance between their centers, and it's squared. And a lot of people forget that square. So that's a thing, and this is how you would calculate that force. And here, if you have a positive and a negative, then technically speaking, your force would end up being negative, right? That means that they would attract. Now, what if I made these both positive? Right? Well, now they will be repelled, and our force would be a positive force. We usually don't put a negative I usually leave out the minus or pluses, and I make this just absolute value because most questions are asking for magnitude only. Last deal here is there was an equation that we looked at earlier in the year. It was actually in the fall, and I'm hoping you guys will recognize this. Instead of FE, it's FG. That is the equation to calculate the force due to gravity between two things. So instead of Q's, which are charges, you have masses. R is the same deal. It's the distance between their centers. And you got to square it. Instead of big K, it's big G. And big G here is 667e negative 11. It's a very small number. So this is basically proof that gravity is a very weak force and the electric force is very strong. It's actually billions and billions of times stronger, e to the 9th versus e to the negative 11th. So this is why we humans don't have a lot of gravity, a lot of force there. Electric forces are really responsible for holding a lot of things together. So that's why they're very, very strong. All right, last thing. Let me make it big again. Okay, last deal. We were talking about electric field strength. This is our equation, right? We're going to make this a bit more specific. So we know electric force is this, which means I can take all this, plug it in there. So my electric field strength plug it in here, I get this disgusting thing. What happens, one of the Q's cancels, and so electric field strength is equal to KQ over R squared. And that's really your equation for electric field strength. There we go. We're going to talk about some example problems next and how vectors really come into play here, which takes people by surprise.